This is going to be a video on stoichiometry. Stoichiometry is basically chapter 9, and it's a good chapter because it takes into consideration almost all the concepts we've learned so far in this course and brings them all together for a final, obvious purpose. So what I've done is I've written down the equation you have from page 3 in your booklet. I'd like you to read page 3 and 4 first, pause the video and come back, please. Okay, this is the equation in the middle of page 3. If you look at this equation, an old kind of skill, so to speak, would be to identify what kind of reaction it is. First of all, you'd say to me that it's chemical because it contains one reactant breaking down to two or more products. You could say that it contains a reactant that's binary ionic and breaking down to two elements in this case. You identify that one of the elements on the product side is a diatomic. All kinds of things you could say. Based on chapter 6, we start to do about compound types, and then in chapter 7 we talked about skeleton equations. Now this equation is balanced, a chemical equation, and the reactants, which is only one, so we learned that basically for every 2 moles of chromium 3 oxide, we would break it down probably with heat, maybe even electricity. We would get 4 moles of chromium and 3 moles of oxygen gas. That equation basically describes a recipe, so to speak, of how the reactants and products come about. So we have 2 moles of reactants. We're going to get 4 and 3 moles of products, chromium and oxygen respectively. It's not very often, however, that we work with whole numbers of moles in a lab. So here's a typical question. If you had 725 grams of chromium 3 oxide, you may want to figure out, based on the theory, how many grams of chromium you could produce. Let's just say chromium was a precious metal. You wanted to sell it. This is an application of stoichiometry, figuring out how much product you should be able to get based on the starting amount. So our job in this chapter is going to be able to learn how to convert from one quantity to another based on the initial recipe, the initial balanced chemical equation you're given to start. There are certain steps that will help you get through this process and make it easier. The first step is always to write a balanced chemical equation. This part's already done. The second step is to decide on a plan or path, and that'll mean you'll have to be organized in how you set up your information, how you organize your calculations on your page. Instinct is not going to work very well in stoichiometry. You're going to get lost. It's highly recommended that you use a systematic approach. The next thing you need to know, be reminded of, is the fact that the grams of one substance into moles is not the same type of calculation as the grams of another substance into moles, because substances have different molar masses. So you can never ever change from grams of one substance to grams of another directly, because they do not have the same molar masses. It's going to require us to use moles, us to use how the substances behave in the recipe to figure out how the actual amount of grams can be calculated. That's getting a little ahead of ourselves, but as I was saying, the steps are going to be to write a balanced chemical equation, pick a path, and then you're going to want to set up your calculations using dimensional analysis, like we learned in chapter 8. And at the end, you're going to want to ask yourself if your calculations are reasonable. On page 4, you were asked to read that information, and let's talk about what it says. It says the chromium 3 oxide decomposes in a 2 to 4 to 3 ratio. That's pretty straightforward. 2 to 4 to 3. It also says the number of atoms of each element can be determined. Well, of course, there's 4 atoms of chromium left and right, 6 atoms of oxygen left and right. You could describe this reaction on a microscopic level and say 2 formula units of the compound break down to give 4 atoms of chromium and 3 molecules of oxygen. But how practical is it to work with those kind of quantities? It's very impractical. So we often talk about the bigger sizes, the quantity of a mole, which is not a huge amount physically unless you compare particle numbers, but in terms of sizes, in terms of grams, very practical. 2 moles of chromium 3 oxide will decompose to give 4 moles of chromium and 3 moles of oxygen gas. The second example is the reaction for the formation of ammonia. And this equation says on a microscopic level, it's a 1:3:2 ratio. 1 molecule of nitrogen reacts with 3 molecules of hydrogen to give us 2 molecules of ammonia. We could take that number, that ratio, and we could multiply it by a higher amount. We could say 15 molecules of nitrogen would react with 45 molecules of hydrogen to produce 30 molecules of ammonia by multiplying every coefficient by 15. We could say 1 mole of nitrogen, or Avogadro's number of particles, would react with 3 times Avogadro's number of hydrogen to produce 2 times Avogadro's number of ammonia. And of course we could always explain our 1:3:2 mole ratio. 1 mole of this, 3 moles of that, will produce 2 moles of ammonia. What you have to remember from chapter 7 is in a balanced chemical equation, the number of atoms will always be equal left and right, and the mass of the reactants will always equal the mass of the products. The number of molecules won't necessarily be the same left and right. The moles won't necessarily be the same left and right, but the atoms will always be conserved, and the mass will always be conserved. In your booklet, page 5, chapter 9, you're going to see a heading that says mole ratio. This is the newest and main conversion factor you have left to learn to be able to do stoichiometry. Top of the page, you're going to see this example, and what it really says is 4 molecules of ammonia reacts with 3 molecules of oxygen to produce, and we want to finish that statement. So we're going to say it's going to produce 2 molecules of nitrogen gas and what else? 6 molecules of water vapor. And that is basically a relationship of how these reactants and products come together. So 4 molecules and 3 molecules produce 2 molecules and 6 molecules. Again, that's microscopic and not very practical. We could take any variation of that, keeping it proportional. We could say, for example, 20 molecules of ammonia. So that if you look at the comparison between the given amount, which the ratio is 4, and now all of a sudden we're going to have 20. That's 5 times bigger. So the rest of our statement would have to be 5 times bigger. We would need 15 molecules of oxygen to finish our sentence, and that would produce 30 molecules of nitrogen and 5, I screwed that up. That should be 10 nitrogen because it's 5 times bigger. 10 molecules of nitrogen and 30 molecules of water vapor. Everything is 5 times bigger based on changing your proportion. Now the key though, and the best relationship for any balanced equation is not really molecules, but actually about moles. The best conclusion you could make would be to say this: 4 moles of ammonia, because it's practical in terms of quantity, would react with 3 moles of oxygen to produce 2 moles of nitrogen and, of course, 6 moles of water vapor. So the question becomes, how do we take the balanced chemical equation and use that for our further purposes? And you need to be able to write a ratio for any two things from a reaction. So what do I mean by that? If you were going to compare ammonia and oxygen, let's just say, then you could do many things. You could say, for every 4 moles of ammonia, you will need 3 moles of oxygen. You can write that upside down, so to speak, and say, for every 3 moles of oxygen, you're going to need to use up 4 moles of ammonia. You can compare oxygen and nitrogen, a 3-to-2 ratio. You can compare oxygen to water, a 3-to-6 ratio. Water to ammonia, a 4-to-6 ratio. Which ratio that you pick will depend on what you're given in your question and what you want to find for an answer. This will only make sense when I do an actual question. So I'm going to skip ahead to the next slide, which has an equation from the top of page 6. This is the reaction for the formation of water. On your page, it's not balanced. I already balanced it by putting a 2 in front of the water to balance the oxygen, and then a 2 in front of the hydrogen to balance the hydrogen. Now, what can we say about this reaction based on this information? Well, many things. Part A on page 6 at the top asks you to write a mole ratio comparing oxygen and water. Looking at what I'm given, and I've got a 1 in front of the oxygen and a 2 in front of the water. So I'm going to complete the part A. I can write a mole ratio 2 ways. I can say 1 mole of oxygen is used up and 2 moles of water, like so. But I could also write that mole ratio upside down, so to speak, and I could say 2 moles of water for every 1 mole of oxygen. And which mole ratio that you pick, it's always going to be 50-50. It's always going to be one way or the other. Which one that you pick will only depend on what you want for units to cancel. So whatever you want to cancel should go on the bottom. Whatever you want to find should go on the top. So for part B, just to reiterate one more of these types, part B asks for a mole ratio comparing hydrogen and oxygen. Well, the mole ratio is a 2-to-1. I can write 2 moles of hydrogen for every 1 mole of oxygen. Or I could write 1 mole of oxygen for every 2 moles of hydrogen. And again, it would depend on what the question's asking you to do. This will be a lot easier when you see an actual real question, not just a bunch of hypotheticals here. And examples 1 and 2 on page 6 give you actual examples. So bear with me for a few more minutes. Okay, example 1, the equation's given and it's balanced. So it says for every 4 moles of ammonia, you need 3 moles of oxygen. It's going to produce 2 moles of nitrogen and 6 moles of water vapor. That's the recipe. 4-to-3 to 2-to-6. Now the question becomes, if you have 3.2 moles of ammonia, below the ammonia I'm going to write 3.2 moles. That's where that goes. And below, what am I trying to find here? Yes, there's sufficient oxygen, so there's lots of oxygen. How many moles of water? Ding, ding, ding. The water, I'm going to put a question mark. I'm going to put the word mole. That's what I want to find. Now you have to say to yourself, can you change from moles of one reactant to moles of another reactant directly? And the answer is yes, because we know how they behave in the balanced chemical equation. We know it's a 4 to 6 ratio. So to do these questions, they're simple if you're organized and if you use your units. If you don't, you're going to find them more challenging. So write down what you're given on the far left, and I mean the far left. 3.2 moles of ammonia. That's my starting amount. I want to change that into the amount of water. The recipe says for every 4 moles of ammonia, I'm going to get 6 moles of water. So then your decision is going to be where do you put the 4 and where do you put the 6. What you want to find goes on the top. You're going to put 6 moles of water on the top because that's what you want to find out about the water. And the recipe says you will use 4 moles of ammonia to do it. Now mathematically, to complete the question, if you check out your units here, moles of ammonia are going to cancel. Into your calculator, you're going to type 3.2, times it by 6, and divide it by 4. You will notice I did not reduce this ratio. The ratio should always match the stoichiometric coefficients, the coefficients in the equation. We're going to use those for stoichiometry, so they're called stoichiometric coefficients. You should never reduce those. This is the mole ratio, and that comes from the balanced equation. So mathematically, your calculator is going to say 4.8, but you need 3 digits. So 4.80 moles of water is the math answer. Is it reasonable? Well, if you had 4 moles of ammonia, you would get 6 moles of water. If you have only 3.2 moles of ammonia, then it goes without saying you're going to have less than 6. And 4.8 seems very reasonable. The second example involves a combustion reaction. And it says, determine the moles of oxygen. So ding, 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 how many moles? Right away I put a question mark. Of oxygen is required to burn 2.4 moles of ethane. 2.4 moles of ethane. That's my starting amount. I can change of moles of one to moles of the other if I know the stoichiometric coefficients. Look at this reaction, it's like, oh, it's not balanced. You should pause the video and balance the equation for practice. You're going to get 2746 for your balanced chemical equation. Let's write down what we know. Write down what we're given. On the far left, 2.4 moles of ethane is what the question gave us. The recipe says 2 moles of ethane requires 7 moles of oxygen. We have more than the recipe. We're going to get more than 7 for our answer. Now your job is to look at the balanced equation and identify the mole ratio. Well, it's pretty easy. It's reacting in a 2 to 7. Your only decision is which way do you arrange your fraction. On the bottom, what you want to cancel. So you want to put moles of ethane in the bottom, and that number in the equation is 2 in the front. So 2 moles of ethane is going to react with 7 moles of oxygen. So mathematically, you're going to take 2.4 and multiply it by 7, and then divide it by 2, and that should give you the right answer. Notice the units. Moles of ethane cancel. You're left with the desired unit of moles of oxygen. So 2.4 times 3.5 is going to give you 8.4 moles of oxygen. And that is reasonable because it's greater than 7. A little bit bigger, and that's going to be the final answer. 3 significant digits, 8.40. This is what we call a mole-to-mole stoichiometry because you're converting from obviously moles of one to moles of the other. You can do that directly if you know the recipe. Well, of course you're going to know the recipe. That's what the balancing equation tells you. However, the big but, practically speaking, you're not in a lab going to work with moles. You're going to work with something on a scale, grams. So our next job is going to be to figure out how do we convert from grams of one substance to grams of the other, knowing full well that the grams cannot convert to grams because they don't have the same masses. And that's where the more complicated stoichiometry comes in, but it's not difficult. So, that's the next lesson.